Hi, so in this video, I want to look at finding the derivative of the exponential function. So the derivative of the function f of x, which we're going to define as e to the power of x, which also can be written sometimes as x of x. So the exponential function. So when we want to differentiate this e to the power of x, or this exponential function, it depends on what definition of the exponential function we use. And there's actually multiple equivalent definitions of what the exponential function is. I'm just going to pick three interesting definitions, or probably the three most simple definitions of the exponential function. And we're going to prove that the derivative of e to the power of x is indeed e to the power of x itself. So let's start with this first definition. So one way that you could define this exponential function is by this. So e to the power of x is the solution to the differential equation d f of x by dx equals f of x with initial condition f of 0 equals 1. So that's one definition that we could use. Just move this down. Just right here, definitions or potential definitions of the exponential function. And as I said, all of these definitions are equivalent, but I'm not going to prove that they are equivalent in this video. Okay, so that's one possible definition of the exponential function. So the solution to this differential equation with the initial condition f of 0 equals 1. Another possible definition is this one here. So e to the power of x is defined as this summation. So we'll start from n equals 0, and we're going up to infinity. So this is an infinite sum, and it can be defined as this. So x to the power of n divided by n factorial. So I mean, this is just equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on. So again, definition number 1 and definition number 2, these are equivalent definitions of this exponential function. Or you could also define this exponential function using this kind of definition. So e to the x is the function such that, so st stands for such that e to the x minus 1 tends to x as x tends to 0. So that's another potential definition you can use. Yeah, there are at least 2 or 3 other definitions that you could use to define what this function means, but we're just going to pick these 3 definitions here. And from these definitions, each one of them, we're going to prove that when you differentiate with respect to x, e to the power of x, we're going to get e to the power of x itself. So that's what we want to prove. Okay, so if we start with this definition number 1 then. So proof that d by dx, v to the x, equals e to the x using definition 1. Okay, so definition 1 stated that f of x equals e to the x is the solution to the differential equation df by dx equals f with the initial condition that f0 equals 1. Okay, so I mean, what this means, this differential equation, is that when we differentiate this function, we get e to the x itself. We get the initial function itself. So we can just test this out. So if we substitute x equals 0 into our function, what do we get? So we get f of 0. Well, anything to the power of 0 is the number 1. So this has to be the number 1. So yeah, that satisfies this initial condition. So we know that e to the x works with the initial condition. So that's the first thing we need to check. And okay, so when we differentiate this this function e to the x, we're supposed to get e to the x. So by definition, if that is the definition of e to the x, then that is the function e to the x. So f is going to be e to the x. And so therefore, when you differentiate with respect to x, e to the x, you get e to the x, because it satisfies the initial condition, and because from our definition, if f of x is e to the x, and this is our definition, then it must be true that when we differentiate e to the x, we get e to the x. So this is quite a trivial one. Not really much proof to be done there, other than just checking the initial condition works. So yeah, that's kind of a very rough proof of the first one, just by using the definition of this definition in number 1. So now if we try to prove that this derivative is true using the second definition, so using like this summation definition, so proof using definition 2. Okay, so this time we're defining e to the power of x as this summation 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and this is going on infinitely. So just by simplifying this, we're going to get 1 plus x squared over 2, because 2 factorial is just 2, and then 3 factorial is 6, so x cubed over 6. And then we'll do another one, so x to the power of 4 over 4 factorial, but that's going to be 24, and so on and so on. Okay, so when we want to differentiate e to the x using this definition, so we can just use our differentiation rules from our from the first video that I did. So if we want to differentiate the e to the x using this definition, we're going to be differentiating all of this summation. And so on, so on, so on. Okay, so that's what we want to differentiate. Just make this all a little bit smaller. Okay, so we're going to be differentiating this expression within there. So again, using the linearity of differentiation, because differentiation is a linear operator, we can just differentiate each of these terms one by one. And as I said, using the first lesson, also video that I did on differentiation, we can just use the fact that when we differentiate x to the power of n, we get n times x to the power of n minus 1. So using that that result that we found in the first video, we can differentiate each of these terms. So the derivative of just the number 1 with respect to x is 0. Derivative of x with respect to x is 1. Derivative of x squared over 2 with respect to x, that's going to be just an x. Derivative of x cubed over 6 with respect to x, so that's going to be x squared over 2. Derivative of x to the power of 4 over 24, so that's going to give us an x cubed over 6, and so on and so on. And actually what you're going to notice is that if we keep on going forever, an infinite amount of times, this expression there, I mean, we could ignore the 0 there, because that's not needed. But this expression down there, this derivative that we've calculated, is exactly the same as this up there. So our original e to the x. And so what we've kind of shown here is that when we differentiate e to the x, we get exactly the same summation as the original e to the x function. And so, again, not really a very formal proof, but I think we can see from this that when we differentiate e to the x, we literally just get e to the x itself. And so, again, let me just make my writing a bit smaller. So what we eventually get is, once again, the summation from n equals 0 to infinity of x to the n over n factorial, which is itself e to the x. And so therefore, when we differentiate e to the x, we get e to the x itself again. And so, yep, so using this definition number 2, we've proved that this e to the x has a derivative of e to the x. Okay, great. So now, if we look at this last definition then, and using this last definition, we now want to prove this again. So e to the x is the function such that e to the x minus 1 tends to x as x tends to 0. Okay, so if we assume that this is the true definition of what the exponential function is, let's use the actual definition of differentiation to see if we can try and use this definition to prove the result. So again, using the definition that we've used in all of the previous videos, so if we let f of x equal the exponential function, then we know that the derivative, just by the definition of what differentiation is, this is the limit as h goes to 0 of f of x plus h, subtract f of x, all divided by h. So what we can now do is just plug in our exponential function into this differentiation, or into this definition, I should say. So this is going to be e to the power of x plus h minus f of x, which is e to the x itself. And this is all divided by h. And again, we can do some simplification. So if we look at that numerator, this is e to the x times e to the h, because this is just indices, using indices rules. Subtract e to the x, and all divided by h. And then what we can do just now is just factorize out that e to the x. So we're going to get e to the x multiplied by e to the h minus 1, and this is all divided by h. Okay, so we've got that. So now if we go back to our definition of what e to the x is, using this definition number 3, so this tells us from the definition that this function is the function that satisfies this condition. So e to the x minus 1 tends to x as x tends to 0. Okay, so let's just change the letters with this then. So using definition 3. So this definition said that e to the x minus 1 tends to x as x tends to 0. So if we just change the x to an h, so e to the h minus 1 tends to h as h tends to 0. So what does this mean? So e to the h take away 1 tends to h as h tends to 0. So what that means then is that when h is a small value, this function here is essentially the same as this function here. And so when you divide two functions or two numbers by each other, which are essentially the same, you're going to get the number 1. So what this is saying then is that e to the h minus 1 over h is approximately the number 1 for small h values. So if that's the case, then what we can say from here is that the limit as h goes to 0 of e to the h minus 1 over h equals 1. Now, if you go back to the previous slide, so we've now just determined using the definition that if this definition is true, then this limit down at the bottom here must be true. So if that is true, then if we look here, we've got the limit as h goes to 0 of e to the h minus 1 over h. We've determined that is 1. And we've got the same fraction over here, e to the h minus 1 over h. And we know that that tends to 0. So with this e to the x there, we've got no h's in there, so we can just bring this e to the x to the outside of the limit. So you've got the limit as h goes to 0, e to the h minus 1 over h. And we've just determined using definition number 3 that this limit is 1. So what we've got then is e to the x times by 1, but we don't need to obviously put that times by 1 there. So what we've just proved is that the derivative of e to the x is once again e to the x. And so therefore, the conclusion from this is that when you differentiate e to the x, again, you get e to the x. So the whole point of this video is to kind of say that no matter how we define it, no matter what definition we give this exponential function, we can prove that when we differentiate it, we get e to the x, the function itself. So that's why this function e to the x is a special type of function, because yes, when we differentiate it, we get the function itself. And as I said at the start of the video, so there are other definitions that you can use, but these 3 definitions here are probably the most simplest to use to prove. So again, the first one, so if we define e to the x as the solution to this differential equation there, then what that means is that when we differentiate e to the x, we get e to the x itself by definition. And if we just substitute that initial condition, we can check that that initial condition is satisfied. And so yes, this e to the x must have a derivative of e to the x. Using this second definition, so this was just like an expansion, a series expansion. When we differentiate each term and when we add them up, again, we get exactly the same as the expansion we started with up there. And so therefore, this shows us that the derivative of e to the x is e to the x. And using this last definition, we just had to do a little bit of analytical reasoning to explain that the limit as h goes to 0 of e to the h minus 1 over h is 1 from this definition number 3 up here. And from that, using the original definition of what differentiation is, we can then prove that e to the x has a derivative of e to the x. And yeah, that's it for this video.